So all the material I looked at regarding the B trees and the B plus trees has been purely theoretical and very hard to put in practice when it comes to actual real production database systems and linking those two in practice. You know, what you studied in university shows you how to do the math of the B tree and how to traverse. But when you actually know how these things work and used in actual database systems such as Postgres or MySQL or MongoDB, then you're gonna understand the proper path a query takes in order to be optimal using a particular index. So in this video, I want to shed a light about B trees and B plus trees, the evolution of B trees to B plus trees, specifically with regard to production database systems. So if you enjoy this stuff, let's just jump into it. We need to start with the problem. The problem is what we call full table scans. What are those? This is the slowest form of scans. In order to find a particular item, we need to scan the entire table, and that's the original problem that spurs the rest of the discussions here. Then we're going to discuss the B tree, or stands for balanced trees, could be stands for Boeing tree, because that's the research lab that spurred that paper, or can stand for Bayer tree, which is the name of the author of the paper, one of the authors at least. And we're going to talk about the B tree limitations, the limitation of the original proposed B trees and how it was kind of changed and varied to this B plus trees, which is mostly used in all database system. I didn't see any database system use pure B tree and its original, although when you read the papers, when you read the documentation, they refer to it as B tree because that's what it's known, but in fact it might have been B plus tree. And we're going to discuss these discussions. We're going to discuss some considerations when it comes to B plus trees. All right, just discussions and learning the intricacies of the B plus trees, right? Memory usage, storage, stuff like that. And then we're going to talk about how B plus tree storage cost varies in MySQL, specifically AnyDB, because MySQL is a database engine specific, because you can swizzle the database engine underneath MySQL to be anything really. You can put it as a CSV storage, you can put it as AnyDB, that's the default, you can put it as MyASM, you can put it as LSM trees like MyRocks, RocksDB, stuff like that. And we're going to discuss Postgres because these are the most databases that I'm familiar with. I also know a little bit of SQL Server. I'm going to throw in some SQL Server, Oracle stuff, knowledge like that. I'm going to summarize the whole thing. So this is the agenda of this video. Let's just jump into it. So a full table scan is when you have a large table and you want to find a row in that table, or a couple of rows, not necessarily just one. In order to do that, you need to read the entire table. Reading the entire table effectively consists of reading it page by page, because what is a table really? It's a single data file on disk, or could be multiple data files, and then you need to ask the disk controller to say, hey, give me this portion, and then give me this portion, and then gives me this portion, and then gives me this portion. And these portions, really, we can spend hours discussing this stuff, right? If you are looking at the database, these portions are called pages, and this is what I'm going to refer to them here now on pages. Read a page, but the page has a fixed size. Some databases have variables page size, like in Postgres is always 8K by default unless you recompile the source to be something else. I believe AnyDB MySQL is 16K. So when you do that, you read these pages one by one. But what does it mean to read 8K from disk, right? That's could be translated to a single IO, but when you go to the disk, there is blocks, there's sectors. In case of a hard disk drive, there is physical SSD page, which is a different size, like I believe it's 4K. So that kind of plays into consideration, and we can spend hours discussing that stuff, right? So it requires a lot of IO to read all this table, and then go to the memory and then one by one read these rows and find out, oh, is this my row? Is this my row? Is this my row? Nope. So we need a way to be able to reduce the search space. That's the problem that we have here. So let's take an example here. Find person with ID 5. And usually when you have the ID 5, usually you don't care about the value 5. You want more information, right? So you want to find the ID 5 so you can pull the name, for example. So in this case, you're going to scan all these rows until you find this. And during the scanning, you could have pulled one page, you can have pulled 100 pages until you reach that. And the cost can vary with the amount of pages you read from disk, right? So if I'm going to search the worst case scenario, if the pages, if the row is at the last, right, of the record. And that doesn't necessarily mean anything, to be honest. This statement, it can be incorrect. It really depends on the DBMS solutions. DBMS are not dumb. Even when a full table scan, when they do that, when they have to do that, when they have to skip the index, they do smart things. They do threading. They split the tables in half and multiple thread, and they do multiple workers that work from the bottom and from the up, and they do all sorts of tricks to find the row as quick as possible. Meet BTrees. So BTrees, it's a balanced data structure for fast traversal. So the goal is to minimize the search space. I don't want to do all these IOs to find my rows, right? Did that rhyme? I think it did. So what BTree has, a BTree has a set of nodes, and I want you to focus on this word nodes, right? I'm going to reference the paper, the BTree paper written by those two folks in 1970. A BTree consists of nodes, okay? And a BTree have a degree. We call this degree M by default. And you can choose what degree your tree is, right? And the choice of how big, how small really changes the whole equation. And databases pick that automatically, by the way, for you. You don't have to do, and you can't configure this, to be honest. So this degree is basically correspond to the number of child nodes each node can have. I said some in this case because not all nodes can have children, and I don't really care about these details. These are all theoretical stuff. We don't really care about it, to be honest. We really care about the essence of BTree, to me, the traversal aspect of this node. And a node has up to m-1 elements. So if your node has m children, then it has what we call m-1 elements, right? So if it have 5 children, it must have 4. If it have 3 children, it must have 2 elements. So you might say, what is an element? This is a good question. So each element has a key and a value. Very critical thing. So we have nodes. Nodes have child nodes, and each node inside it has elements. And these elements correspond of keys and a value, a key value. The value here is usually the pointer to the row. It's called a data pointer. They call it the value sometimes. In the paper, it's referred to as alpha I, right? So if you read the paper, I'm going to reference the paper in the show notes here for you to check it out. And the slides will be in the show notes as well, guys. So you can take a look at that in the description. The value has the data pointer to the row, and the key itself is what you're searching for. And we're going to show an example to clarify all that stuff. So the data pointer, this is where databases can shine. Each database system does this differently. A data pointer, which is the value here, can either point to the primary key if you have a secondary index, or it can point directly to the tuple. Secondary indexes in AnoDB and MySQL and Oracle, I believe, point to the primary key, while in Postgres, all secondary indexes point to the tuple directly. And just that, I talked about this in my YouTube channel, discussing how Uber moved from Postgres to MySQL, and that is one of the reasons, one tiny reasons. Check out that video if you're interested. Just type in YouTube Uber MySQL Hussein, and you're gonna find the video. It's a very, very interesting read. So there's also this concept of root node, an internal node, and a leaf node as well, right? And we're gonna describe what all these means. Like the root node is very self-descriptive, right? It's the first node at the top. Internal nodes are below it, and the leaf node are at the end, right? There is no child. They don't have children. A very important concept here, a node is equal a disk page here in databases. Most databases, I know in computer science, they give you this contrived example where, oh, a degree of 3 or degree of 5, and they have put some values here that doesn't really correspond to anything practical, right? But practically, a node is a complete page. So if a page is 8K, you better find a way to fit 8K worth of elements in it, right? So that's what we try to think here. So let's take an example. So here's my table here, and you can see that I added another column here to correspond to the internal tuple ID, or sometimes some people call it RID, row ID. The page number sometimes is baked into the tuple ID for simplicity reasons, but here's the tuple ID. It's internal, it doesn't show it, right? This is the physical, the logical primary key or logical field that you have, and this is just a name. So now one choice, and this is what Postgres does is actually that, right? This is my BTree here. Let's look at the definitions here. The node is this red thing. So this is one node, and it has 2 elements, and this node has 3 children. And because it has 3 children, how many elements should it have? 3 minus 1, just 2, right? So if it has M, it has M minus 1. If it has K children, it has K minus 1. That's the definition. And each element has 2 things. It has a key, which is what you search for. In this case, you're creating, let's think about this as an index. You're creating an index on this ID field, right? So we store the keys as these values, right? As these keys in the key space of things, while the value becomes the tuple that points directly to the row here. So key value, also called as data pointer. And you might say, Hussein, I never actually seen this before. All the BTrees I looked at, there is no pair, there's only one value. And I blame the author of this paper, to be honest. It's like when they originally just drew the keys, although the values or the data pointer are inside, but they chose not to. And here's a blurb of that proving this. In the figure, the A, which is the value pointer, are not shown. Why? Beats me. It just, all the papers, all the books, nobody talks about this. They just show this, and it confuses B trees from B plus trees, which is very confusing because that's not the actual representation of the tree. To me, that is the actual representation of the actual tree on disk, if you think about it, right? So anyway, because why am I hammering on this point is because it's very critical to understand that the keys and the values exist in all nodes in a B-tree structure, and that is important for memory efficiency. So let's read through all this stuff right here. So one more thing here. So this root node has a value has two elements, 2 and 4, right? And elements nodes that is less than 2 goes to the left of that element, right? This is the children. Child nodes between the 2 and 4 goes here. Child nodes greater than 4 goes to the right, right? And that's why the trick is like it has to be m-1 for this to work. Let's search for ID number 3. So searching for ID number 3, you're gonna read this node, which is almost one single IO on disk, and think of this really on a real production database. This is gonna have a lot of elements, to be honest. It's not just one. Okay, so it's just gonna have thousands of elements because we want to fit it in single page. So there's so much stuff we can put here. Okay, and then I'm gonna read this and I'm gonna ask my question: where is ID number 3? Well, 3 is between 2 and 4, so I just eliminated this and I just eliminated this. So I'm only gonna pull the pointer, the page pointer, or the something called the child pointer to this row, right? So I'm gonna take, so there is another thing that I didn't show here, but it's shown as a graphic here, right? Which is this pointer. So there's another value that we store here, which takes space. I'm putting it all the way here. So pull, go there, and I just found 3. Now I'm not finding 3 for the sake of 3. I really want 703, right? So if I find 703, I jump and get the value. And even we're not really, 703 is useless here because you're gonna do a full table scan to find 703. There is more information in 703 that tells the database which page actually to pull. It's not gonna fetch the entire table. Is going to fetch the exact page which has 703. So it can have more than 703. It can have 702, 701, anything nearby, right? So finding 1, similar. 1 is less than 2, goes to the left. I cancel these, right? And then get 701, jump there. 5, very simple. Go here, jump, and then go to 705. We can add and delete keys very similarly, and I took this from University of San Francisco. I just animated this with a JavaScript, right? Just adding elements, right? I'm adding elements from 1 to 11, and you can see value 1 at 2, and this is a degree of 3, by the way, right? Which means it can have up to 3 children and up to 3 minus 1, 2 elements, sorry. So we have 1 and 2, add 3, so we split the root and then go here. As we add, we can see we're splitting the pages, and that split also has a cost, right? That's why you don't want to split pages so often. That's why the m value should be so large that you don't really need to split as often. Okay, and these, the order of elements here also matter. If these are random, the inserts will be slower, if you think about it, because you will the randomness will cause the pages to be stored in an unordered manner. And if you added a new element that has to go into the page or in an order fashion, then you have to split the page. Split the page is expensive. So this is just a side effect of things. So this is how you add it. All right, and I'm not gonna go through the actual theory of adding and deleting and splitting. Really, it's not. I'm not interested in that. So here's the same tree that we're looking at that we just added, animated, and it's very critical to understand. This is the internal nodes, right in the middle. These are leaf nodes, and these are root nodes, right? We can follow this tree essentially. It was like, okay, the 10 is greater than that. That's why you see the values of 10 here, right? And then 9 is less than 10, and 11 is greater than 10. So you can search very efficiently here. And imagine this is expanded to thousands and thousands and thousands of nodes, right? You can see the value of that. Okay, what's the limitations of BTrees? BTrees are not perfect. That's why it was a variation was created to solve these limitations. So well, the first problem is elements in all nodes store both the keys and the values, right? And because you store the key and the value in every single node, then you can only store so many elements. Because let's go back here and see. Here's why. If I'm reading this node, right? If I'm reading this node or this page, because they are effectively the same thing in a database, then you're going to pull keys 4 and 8 and their corresponding values. So if you're searching for the key 1, you really just used the key, you didn't use the values. So you wasted precious memory space that you didn't really use, if you think about it. So alternatively, if I'm storing the values in the page, in the node, then these values are not just this could be up to 64-bit. So, or some people store GUIDs. So think twice when you create an index on a UUID or a string, because that puppy exists right here, right? Like if you create, for example, a primary key, right, on a string field, then this string values are stored on everyone. B+3 store them in a leaf throw, which we can discuss, but they are stored. And when they are stored, they take more space. More space means I can fit less elements in a page or in a node. And if I fit less element, that means I need to read more, right? Because I need to put more nodes. More nodes mean more pages. More pages means more I/O. More I/O means slow. So that's the trick here. Elements in all nodes store both key and value, so they take more space, thus require more I/O and can slow down the traversal, right? So that's the trick here. So we might say, well, what else? If you don't store the value, you need to store the value at some point, right? Well, we're gonna talk about that. Another limitation of the BTree is range queries are slow because of the random access, right? Because you're jumping and back and forth. If I ask you, give me all the values between 1 and 5, and we're gonna show you an example in a minute. Then we're gonna jump all over the place to find 1, and then find 2, and find 3, and find 4, and then find 5, right? I have to do 5 different traversals to find these values. Not necessarily, it might be a little bit less if you were lucky, but that's what I need to go. It's almost random, right? Despite them being very tucked next to each other. The keys, right? Give me all the, should be keys, not values, but you get my point. I'm searching for these values, these keys effectively, right? But B+3 solve both these problems. Another problem with this is like it's hard to fit internal nodes in memory when you have all these values, right, in each element. Because you have all these values, then I can't really fit stuff in memory, especially like, I don't know, if I have like a primary key on a UUID field or on a string field, right? Then it becomes very expensive to store this index or this BTree in memory because it costs a lot, right, to traverse. Let's take an example of why BTrees can be bad for range queries. So I'm gonna now find all the rows ID between 4 and 9 in this particular BTree. So I'm looking for 4 and 9. I want to pull all these rows so I can look up Pete, Edmond, Ion, Edmond, Sarah, and so what I'm gonna do is, okay, let's search number 4. Oh, we were lucky, we found number 4. Okay, let's find number 5. Where is 5? Well, 5 is between 4 and 8, so we jump to this data pointer, child pointer, and find to this page pointer and get to 6. Or well, 5 is actually less than 6, so let's jump another IO. So 1 IO, 2 IO, 3 IO. We found 5. Okay, let's go ahead and find 6. Well, 6, we just actually read it in a minute ago, so it's in memory hot, right? Unless we had to throw it back into the disk for LRU reasons, least recently used cache, like if we throw it back. But it's there. Okay, we found 6. So how about 7? Go and find 7. We found it. All right, how about 8? 8 is, oh, there you go. It's up on the road. How about 9? 9 is in this side. Go here. We read this page and then go on and then to the left. This is 9, and then we find the value of 9. So look at what we have done to find this. And you might look at this like, it's not that bad, but we thrashed the index to look for these 5 values. Despite them technically being next to each other, they are sorted. They are next to each other, right? And that's another thing that BTree solved. Another thing BTree solved is like it tries not to put values in these kind of hot searches. It tries to make this as slim as possible to search and pushes all the data to the leaves, as we can see in the minute. So BTrees, it's exactly like BTree, but only stores the keys in internal nodes and obviously the root as well, right? For some reason, I think internal nodes also kind of include the root. I believe there is a little bit of a nuance of difference, but who cares? It's the same thing, right? If we think about this, values are only stored in leaf nodes. Very critical here. So now these internal nodes and the root node are slim, which means I can fit more keys in my nodes, right? Because I don't need the stinking data pages and values anymore. I just need to store my beautiful keys, right? So one IO to fetch one node, right, which is one single page, will give me way more elements, way more keys than it would have gave me if it was a simple BTree, because I had to I have the burden of the actual B plus, the values and the data pointer, which most of them will be tossed, unfortunately, during the traversal. So internal nodes are smaller since they only store keys and they can fit more elements, as I discussed. Here's another important thing, but not all databases actually implement this, but it's very interesting. Leaf nodes are linked. That's what helped range queries, by the way. They are linked. So because all the values are stored in the leaf nodes, they are also linked. Each one points to the next leaf node. Each one points to the next leaf node, and so on. So once you find a key, you just found everything after it and everything before it. That helps range queries so much. It's great for range queries. Here is a BTree of a degree 3. So look at that. So you can see now we're only storing the key, truly just the keys here, right? And the page pointers, right, which is these white arrows. So here's the value of 5. To the left is 3, to the right is anything greater than 5, which is a beautiful node which has the value of 7 and 9, right? 7 to the left is 6, to the right is 10, in between there's 8, and so on. So you can see that the values, the keys are kind of duped. They are duplicated, and we have to do it because the leaf nodes should have everything we need. We need everything in the leaves, including the values. So there are duplicates all the time. Not all of them are duplicated, right? Like 11 is not up here, right? But some of them are, and that's okay. So that's a cost that have been proven to be very minimum, right? To the value we get out of this structure. So now look at this. If I find value 1, if I find the key 1, I can find the value, and there is a nice leaf pointer that points me to the next sorted key directly. So you can just jump directly to the next one, and when you look at this, this looks really terrible in a database perspective, because a single node is a single page, right, as we discussed, and in a single page we have one element only. That's a complete waste. Our pages in actual database speak are large, so you're gonna see so many things here, not just one element. This is a terrible example, but I can't draw a BTree of a degree, I don't know, 1024. It's very, very hard to draw, right? It just doesn't fit here. But think of this have a lot of elements, and as a result, one read gives you a lot of elements and their values, and also you get a pointer to the next one, which has a rich set of other elements that are next to each other. Let's take an example. Find rows, same example that we did for the BTree, but this is for the B+tree. Find all the rows between 4 and 9. So, okay, let's find 4. We'll start for 4. Just start for one of them. Okay, 4. I'm gonna read this row, 1 IO. All right. Okay, 4 is less than 5, so I'm gonna take this. I just eliminated half the tree. More than that, really. I gotta find a 3. Okay, 4 is greater than 3, so I'm gonna take this then. Okay, here's 4, but really, this is still an internal node, so I have to take 4 is equal to 4, so I also go to the right. That's one of the conditions I forgot to mention. If it's equal, greater, or equal, go to the right. And then we just reached here, 4. But guess what? You find 4, you find 5, you find 6, you find 7, and 8, and 9. And if you're lucky, all of this is just a single IO, right? Because this is just 5 elements. Even if it's like, most of the time, like 400 or 500 can fit in a single page. It really depends on the data pointer. What is this type? If it's a short integer, like, I don't know, 4 bytes, right? Then it can fit. You can fit a lot of elements there. If it's a GUID or a UUID or a string or a blob, I don't know, why would you index a blob? But that would be really terrible. You can't fit much stuff there. So B+tree and DBMS considerations. Take a sip of tea, take a sip of coffee, relax a little bit. I know it's a long video, guys, but I think we need to discuss these in details. You can pause the video and come back later. It's all right, right? This is there's a lot of content there. Ask me questions, ask questions as you encounter them. But this is very, very interesting to understand now. So B+trees and DBMS considerations. There's an additional cost here, which is the leaf pointer. Again, for instance, MySQL, InnoDB, and Postgres, SQL Server all have these leaf pointers that points to the next of the next leaf point in the B+tree leaf nodes. Wired Tiger in MongoDB. Yes, MongoDB does use B+trees through this Wired Tiger database engine, which I have a lecture about database engines, right? Talk about that. And Wired Tiger is a B+tree based engine, and also they have an LSM variant, log structure merge tree, that doesn't have this pointer, right? For design decisions, those guys are smart. They only include things where they absolutely need it. So it's like, okay, range queries, who cares? You're not gonna do a range queries in Mongo, for instance. Okay, you're not gonna search for range of keys. Don't do that, right? One node fits a DBMS page, as I discussed. Most DBMSs do that. Can also fit internal nodes easily in memory for fast traversal, because the nodes are now tinier, I guess, right? You can fit a lot of elements, right, in these internal nodes. You can fit these internal nodes in memory easier. So the traversal a single IO will give you way more elements. As a result, it's way faster, right? Plus, these again really depends on what are you indexing on. This can fit in memory. If it's a GUID or UID, it's not as easy to fit in memory, but still can. Usually the internal nodes are not as busy as the leaf nodes in a B+trees. Leaf nodes can live in the data files in the heap. That's absolutely fine. It is obviously you can try to put them in memory, but if the values, right, the value that points to is expensive, then sometimes it's not possible. Most DBMs uses B+trees. So here's an example of the storage cost here. This really, I said should between quotes here, but doesn't have to, right? The BTree index works best when it's in memory, right? So when you load up your database, let's say you have a table with 5 indexes, you can try to put all the indexes in memory, and you can check the sizes of the indexes by doing a query on the database and see, can I fit this entire index in memory? Most of the times the indexes are tiny, like if you don't have large files, but if it's large, some databases make the choice, okay, I'm going to only put the internal nodes in memory so that my traversals are so fast because I cache the page, and these are tiny, right? And not necessarily tiny because these are pages the same size, but I have way more elements, and as a result I can traverse way more. And this could fit in disk, but you can definitely put it in memory. Nothing that stops you from doing that, right? If they fit. Again, it really depends on this pointer, and also depends on what you're keying on, right? Okay, let's talk about this is the final thing, I think. The storage cost between Postgres and MySQL. So B+tree secondary index values, and I talked about secondary indexes versus a primary index difference. It's very important to know this difference, is the difference between the two, right? And can either point directly to the tuple, this is an example of Postgres, or to the primary key. And this is one of the reasons that Uber moved from Postgres to MySQL. So hey, Postgres points directly to tuple. As a result, write amplifications implode. And I have a write amplification lecture. Go to the section where you have like a various database discussion. You can see the write amplification. Very critical to understand that, right? So if you have a secondary index and this secondary index points to the tuple, then the tuple size is really not that large, right? Because it's a fit. I believe it's a 32-bit. I might be wrong. It might be 64-bit, but that is the pointer. While the MySQL secondary indexes point to the primary key. So if the primary key is large, if it's an integer, you don't have a problem really. It's just tiny, right? But if it's a GUID or a UID, that is a really bad idea to put a GUID or a UID as the primary key in AnnoDB MySQL, because any secondary key unfortunately will point to the primary key, and plus the whole thing is clustered, so inserts are so slow because of the randomness of the UID. It's just not worth it at all. Okay, so as a result, the secondary indexes will be so large because they have all these values that points to primary keys, which are effectively UIDs, which are these large things, right? And you can do all sorts of tricks to convert UID into, instead of using a string, which is I forgot what's the string of the UID, but so many bytes, right? 128, I believe. But you can trick it to use like 64 bytes or less than that, using the binary representation of UID. But still, it is still large, right? If it's large, takes space. If it takes space, it can't fit in memory, right? Your memory is precious. You might say, I'm going to add a 1 terabyte worth of memory for my primary database. Sure, but do you have to? Right? Think about this, right? Scaling and the database engineering is not something that you take lightly. You have to think about all this stuff, and it all makes sense when you understand these basic fundamentals. That is what I want to convey in this lecture. The BTrees are not something you do math on. Every decision you make costs you, right? And it is important to understand how these different DBMSs make these design choices, because every design choice can lead to a completely different outcome. If the primary key data type is expensive, this can cause bloat in all the secondary indexes, as I talked about. Leaf nodes in MySQL AnyDB contains the full row, since it's an index organized table or a clustered index too. So that's another thing, right? Clustered indexes in general. SQL Server also have this idea of clustered indexes, clustered index or clustered tables. Sometimes they call it index organized table. So this is this is an index where the index is the table itself. If you think about it, it's just the whole thing. The leaf node has the whole row and all the columns in it, right? So that everything is really clustered nicely. It has disadvantages and advantages, right? I'm just not gonna go through it, but it's very important to understand it. Summary. So here's the end of the video. So we discussed full table scans. This is where the problem originates. I'm searching for a thing, and there's this table is so large. Index it for me. We created BTrees. It has some limitations. We fix this limitation with B plus trees, but there are some considerations, obviously, with B plus trees, because it depends on what do you put the value on and memory consumption. And based on that, the MySQL, Postgres, and other databases make a better design choice. And it all comes back to you. There is no right or wrong in any of these databases. It depends on what you're trying to do, and pick the database that fits your use case as a result. All right, guys, that's it for me today. Hope you enjoyed this video. I'm gonna see you in the next one. You guys stay awesome. Goodbye.